start. 4, 3, 2, 1, 0, and liftoff. The liftoff of the space.
In our natural pursuit of knowledge, space has always mystified and beguiled us. Over the past 5 decades, we've pushed the final frontier inevitably onward into the ether. The cost has been colossal. Now every day, new data, new conclusions, and the thirst for deeper exploration propel us inexorably onward. The advantages of the discoveries made through space travel are myriad, but the fundamental curiosity as to what is out there will always fascinate and taunt us. Come with us now into the unknown and discover the disappearing frontier. 3 British-built cameras on board the European Space Agency satellite will spend at least 2 years capturing invisible rays from distant galaxies, trying to shed light on the violent origin of the universe and its future. Space Station Freedom, the key to a more permanent presence in space, providing research that will revolutionize our way of life. The European Space Agency's cluster mission safely blasted off from Kazakhstan on board a Russian Soyuz rocket. The 2-year mission is to investigate the complex interaction between the Sun and the Earth. Astronauts carry out many tasks, deploying satellites, maybe taking a spacewalk, and even playing with toys. But each of these toys works because of important scientific and mathematical principles. America's shuttle fleet is playing a vital role in preparing people and machinery for a more permanent presence in space. On-orbit testing of new hardware, like this restowable solar array, has helped engineers design lightweight, compact structures for the station. Astronauts also gain knowledge in handling large objects and connecting space station-like components. Even devices for transporting crew members along Freedom's 350-foot truss have been tested. On several occasions, the shuttle's payload bay has been converted to accept Space Lab, similar in design to the scientific laboratories planned for Space Station Freedom. Here, life science experiments focus on the body's adaptation to weightlessness. Without gravity, bones and muscles deteriorate rapidly. Astronauts conduct research to find out why and test possible countermeasures to prepare for extended stays aboard Freedom. Microgravity research gives America a competitive edge in today's high-tech marketplace, providing valuable new developments in such fields as materials, electronics, and biosciences. For example, protein crystals can be grown larger and more uniform in space. Researchers want to unlock the molecular structure of proteins, large molecules that perform key functions in our bodies, so that they can design drugs targeting specific diseases and viruses. Shuttles spend only a few weeks in Earth's orbit, while the space station is designed for a long-term stay. Its state-of-the-art laboratory will house more than 100 scientific instruments, including those to develop better alloys, more efficient semiconductors, and solar energy systems. This research will revolutionize our way of life in the same way the Apollo era gave us technology for computers, laser surgery, long-distance calling, and even ATM machines. Already, prototype components are being built and tested. Engineers are also fine-tuning power systems and simulating the station's demands on electricity. 18 shuttle missions will carry prefabricated sections of the station into orbit, using robotic arms to assist astronauts during assembly. Once completed, a single habitation and 3 laboratory modules will be clustered together, shared by the United States and its international partners, Canada, Japan, and 13 European countries. Freedom's 4-person crews are scheduled to spend 3 to 6 months at a time living, working, and observing from its unique vantage point. The station will regularly be visited by shuttle ferrying food, supplies, and new scientific experiments from Earth. One thing is certain: the key to the future of the space program is tied to the ability to work there on a permanent basis. Station's Freedom a unique outpost built on the strength of America's space program. French Guiana, December the 10th, 1999. The seconds tick away to blast off for the latest mission of the European Space Agency, now celebrating its 25th anniversary. A massive Ariane 5 rocket lifts into orbit the world's most advanced X-ray telescope. It's called Newton after the famous 18th century British scientist. 3 British-built cameras on board will spend at least 2 years capturing invisible rays from distant galaxies, trying to shed light on the violent origin of the universe and its future. They'll help to answer several questions. One is of fundamental importance, and that is, where did we come from? The iron in our blood, the carbon in our bones, was actually fabricated in the centers of stars, and these stars exploded into supernovae. Newton will be able to tell us about the origin of the elements. Some of the first X-ray images of exploding stars and black holes have already started streaming back to Earth, free of dust that obscures pictures from even the best optical telescopes. The mission is the latest part of the science program of the European Space Agency, a collaboration of 14 countries to fund research in space. The agency was set up in 1975 to promote European cooperation in space research for solely peaceful purposes and help develop advanced technology in Europe. Joint funding made feasible space exploration programs that no single country could afford. All 14 countries contribute to the agency's central funds, according to the size of their GDP. This finances the major scientific missions like Newton. Canada also participates in some programs, and there is collaboration with the American Space Agency, NASA, on others. The Hubble Space Telescope, which has been keeping a steady eye on the stars from 600 kilometers above the Earth for the last decade, is an example of just such collaboration. Often thought an American venture, the Hubble carries an ESA-built camera. In return, 15% of the time given to observation goes to European astronomers. This is just one of the space-based observatories ESA is involved with. 5 years after Ulysses became the first spacecraft to fly over the Sun's poles, SOHO was launched in 1995, sitting between the Earth and the Sun. The SOHO spacecraft has been sending back pictures of the Sun's atmosphere in visible and ultraviolet light. Transatlantic cooperation also extends to space shuttle missions. Since 1993, the shuttle has been regularly carrying up into space a special ESA-built space laboratory called Spacelab. Astronauts and scientists have been able to undertake a range of experiments on weightlessness or microgravity. From 1978 onwards, the ESA has been involved in building and launching communication satellites, now in day-to-day use for television and telecommunications. Some of the early launches, though, were spectacular failures, yet this didn't stop the rapid development of a satellite market. This is the latest in satellite technology. Using a new laser-link system, the Artemis satellite is designed to handle both communications and navigation data. Satellites are a big growth area within ESA, but they don't come under the centrally funded science programs. European Space Agency members can decide to join in or not in the development of satellite programs for communication or Earth observation. Climate change, pollution, and other environmental threats like the recent fires in Southeast Asia are best monitored from space. Envisat is the latest ESA satellite for monitoring and measuring changes in the Earth's oceans, land surface, ice caps, and atmosphere. ESA's Earth Observation Center near Rome handles data from over 20 satellites, The agency spends most of its budget on contracts awarded to technology and science-based companies in member states. It's a big incentive for member states to get involved in projects like Earth observation and communications. The sun rises on the biggest space project underway today. The International Space Station is being pieced together in orbit and, when finished, will be the size of a modern football stadium. 10 ESA members are collaborating on the project. The agency's main contribution is in building a ferry vehicle which will be launched every year into space, starting in 2002, to take up food and other supplies to the astronauts manning the station. The European Space Agency is also building a microgravity laboratory called Columbus, the successor to Spacelab. Like all space agencies, ESA has known disaster as well as triumph over the years. The loss of the Ariane 5 rocket in 1996 and the scientific mission it was carrying was spectacular. But Cluster, a mission to monitor the sun's effect on the Earth's magnetic field, has been revived and is due to blast off again. Mars, the red planet of science fiction. A lifeless desert? Or is it? Is there water under this dusty, rocky surface? In 3 years, we may have the answer if the European Space Agency Mars Express lander can probe deep enough. The European Space Agency is about to decide on the next generation of scientific missions that it will be running. A crucial decision, as all members will be committed to what could be long and costly projects. One is expected to be a mission to Mercury, the hottest planet, being closest to the Sun. The other mission which the European Space Agency will consider is called Gaia, and this is designed to measure accurately the positions of 1 billion stars. By monitoring the positions of stars with unprecedented accuracy, scientists hope the mission will show them how the Milky Way, our galaxy, was formed. While these 2 missions are being considered, others are already airborne. Right now, the Cassini spacecraft is flying towards Saturn, carrying a European Space Agency probe which will explore one of that planet's moons. Delving into the history and makeup of the universe, as well as monitoring our own environment and helping communications, these are the twin aims, theoretical and practical, of the European Space Agency as it enters its next quarter century. A tense few moments for the scientists and their families as launch time approached. A day later than scheduled, and 4 years after the first mission dramatically blew up on launch, the European Space Agency's cluster mission safely blasted off from Kazakhstan on board a Russian Soyuz rocket. The 2-year mission is to investigate the complex interaction between the Sun and the Earth. 2 satellites are now in space. A second pair will be launched in a few weeks. They will then link up and travel together in a wide orbit around the Earth, picking up information in 3 dimensions on radiation from the Sun. The Earth's magnetic field protects us from the hot gases, particles and waves that stream out periodically from the Sun, the solar wind. But sometimes they find a gap in this protective bubble. The cluster satellites will fly through the magnetic field and the solar wind to find out what happens when this happens. As the first cluster satellites go into space, the Sun is getting restive and putting out the biggest solar flares for 11 years. Unpredictable solar weather is coming our way. The Soho Space Observatory, which monitors the Sun, has sent back pictures of this latest flare. The white scratches show the damage the solar wind has done to the actual Soho camera. The Aurora Borealis, the northern lights, are the most visible sign of solar weather hitting the Earth's magnetic shield. But cluster should give earlier warning of solar storms, which can seriously disrupt the spaceborne communication systems on which we now rely so heavily. The primary function of the spacecraft we have orbiting our planet is to gather and relay vital information back to tracking stations on Earth. The craft may be working in conjunction with a space station or deploying satellites in the quest to further the knowledge and understanding of mankind. In the course of obtaining this knowledge, the astronauts carry out many tasks. It might mean taking a spacewalk, or would you believe it, playing with toys. Each of these toys work because of important scientific and mathematical principles that are often taken for granted on the ground. Watch what happens when the suction cup releases from the astronaut's hand. You can see the spring jumper take off. Watch it again, look how fast it travels across the spaceship. In slow motion you can see it tumbling off the lockers. The big question with this scene is, will the frog swim as well in air as he does in water? If you watch closely you'll see, no, he doesn't. The astronaut tries several different ways to get the frog to swim in a straight line, but because the air is much less dense than water, the frog will just flop aimlessly around. With this toy submarine, both the propeller and the submarine turn as it floats through the air. In water, of course, only the propeller would rotate. Now if we hold on to the propeller, the submarine turns around it. But when we let go, it takes off. This time the astronaut has attached small pieces of paper to the propeller to make it larger. What will happen when we let this go? Well, you can see it really takes off. Now a pen is taped to the end of the propeller to see if that will change the way the submarine moves. As you can see, it's now far less directional in its movement and much harder to keep under control. This fish can swim really well in water, but here in space he's really struggling and not getting anywhere. However, one thing that will help the fish swim better in air is to increase the size of the fin. It also appears that releasing the fish very gently has an impact on which direction the fish will swim. We finally got it right and the fish is swimming forward. If we release a flapping bird into microgravity, you can see it just flies around in circles. It doesn't seem to have any direction of travel. Look at it again in slow motion. It just goes around, not in a straight line as it does in Earth's gravity. It looks as if it's rotating around the wings. Now if we get it to soar without the wings flapping, it soars across the deck. This time we launch a gravitron to float freely in the cabin. It wants to spin around the wheel inside. To try and get it to tip over, the astronaut bumps it on the top and on the side, but it won't capsize. It's stable about the spin axis in which it was released. That's straight up and down. This is the same configuration, one spinning gravitron, but this time it's been oriented so the spin axis is pointing at the camera. Again, although it's being bumped on all sides, it will not tip. As before, it's stable about the spin axis in which it was released. Here's a graphic illustration of the difference between a spinning and a non-spinning gravitron. You'll notice the spinning gravitron remains stable, whilst the other one tends to tumble end over end because it has no stable spin axis. If we watch it one more time, you'll see that one is spinning, one is not. The one that's not spinning just tumbles free, while the other one maintains the orientation in which it was let go. Now, two spinning gravitrons, which are both stable as they spin. If we take one and bounce it off the other, you'll see that this time, because they're both stable, neither tumbles after they collide. Now a curious combination. Two gravitrons attached together on a wiffle ball. They're both spinning in the same direction, so one would think that they would be very stable in this configuration. But because they weren't perfectly aligned with each other, they got out of hand. Eventually, disastrous results. In slow motion, you can see how the misalignment causes them to break apart. But this time, the two gravitrons are rotating in opposite directions from each other, and because their angular momentum vectors are in opposite directions, their stability axes cancel each other. So in theory, when we let the device go, it should tumble. Obviously, we can't make them both spin at exactly the same speed, so one of them is going to have a little bit of stability. But now we can bump the stack and make it wobble a little bit. As we bump it more severely, there's some tendency for stability, but not as much as a single gravitron had floating on its own. So clearly, the two gravitrons spinning in opposite directions cancel each other. Now we're getting complicated. We have three gravitrons all hooked up to the same wiffle ball. They're orthogonal to each other. That's to say, they're all at 90 degrees to each other. This time, we're going to spin them all in the same direction with reference to their attachment to the wiffle ball. As we do this, you'd expect the angular momentum vectors of each of the gravitrons would add up to a single vector, which would be right between all three. As we release the device, you can see that the only axis it will rotate around is an axis that you could see if you put a pencil between all three of the gravitrons. That is an axis that is equidistant from all three of them. As it continues to spin up, by the natural character of the friction of the gravitrons, it eventually begins to spin so fast that it comes apart. Here's the same combination again, three gravitrons mounted orthogonally to the wiffle ball. Once again, we're going to spin them all in the same direction, but before we do so, you can see how they tumble end over end. There's no stability there because none of them are rotating. Once the astronaut sets the gravitron spinning, you'll notice that initially they begin to rotate around the same axis as before. But one of the gravitrons comes off. And look what happens to the remaining two. They begin to rotate around a new axis, one that's right between the two. Again, they spin at such a speed that eventually the device falls apart. Here's an experiment that demonstrates how a non-spinning gravitron behaves just like a ball on the end of a string. We can change the axis of rotation just as we could with anything attached to a string on Earth. But once we spin the gravitron up, look how it maintains that stability around its rotation axis. We can spin it around and around, and it wants to stay in an orientation so that the spin axis is parallel to the axis of rotation to which the astronaut is holding the string. But when we change the orientation, eventually the gravitron ended up changing the orientation of its rotation, so that it matched the rotation axis of the string. That brings us to the end of this edition. We look forward to your company next time. But remember, we are out there. What we can and can't see is out there, and the mysteries between us, although seemingly insurmountable, are encompassed by a disappearing frontier.